Let's explore dynamic memory allocation in C. We'll be looking at functions like malloc, calloc, realloc, and free. Dynamic memory allocation allows you to request memory during the runtime of your program, providing flexibility in managing memory usage. The illustration shows blocks for each of these memory management calls. The malloc function allocates a block of memory of a specified size on the heap and returns a pointer to it. It allocates uninitialized memory. This means the memory contains garbage values. It returns a void pointer, which you typically cast to the desired type. If the allocation fails, it returns null, so it's important to always check for null after calling malloc. The memory allocated with malloc must be explicitly freed using the free function to prevent memory leaks. Here's the syntax: void pointer malloc of size_t size. For example, to allocate memory for 5 integers, you would write numbers equals int pointer malloc of 5 times size of int. Always check if numbers is equal to null, and if it is, print memory allocation failed and return 1. The memory visualization shows the numbers array with 5 blocks, each allocated but uninitialized, containing garbage values. The calloc function allocates memory for an array of elements, initializes all bytes to 0, and returns a pointer to it. Calloc allocates and initializes memory to 0, unlike malloc, which leaves the memory uninitialized. It takes the number of elements and the size of each element as arguments. Like malloc, calloc returns a void pointer, and you should always check for null to handle allocation failures. The syntax for calloc is void pointer calloc of size_t number, size_t size. Here's an example. Numbers equals int pointer calloc of 5 size of int. Always check if numbers is equal to null, and if it is, print memory allocation failed and return 1. The memory after calloc visualizes the numbers array with 5 blocks, each allocated and initialized to 0. The realloc function resizes a previously allocated memory block to a new size, preserving its contents. Realloc changes the size of an existing allocation. It attempts to preserve the data in the original block. The function might move the memory block to a new location if there isn't enough contiguous space. If the block is moved, the original pointer becomes invalid. Realloc returns null if reallocation fails, so handle it appropriately. The syntax is void pointer realloc of void pointer pointer, size_t size. For example, int pointer numbers equals int pointer malloc of 5 times size of int. To resize it to hold 10 integers, int pointer new underscore numbers equals int pointer realloc of numbers, 10 times size of int. If new underscore numbers is null, print reallocation failed, and return 1. If reallocation succeeds, assign new numbers to numbers. The memory visualization illustrates resizing from 5 to 10 integers. Initially, 5 integers are allocated with values, and after realloc, the block is expanded to 10 integers, preserving the original values. The free function deallocates memory previously allocated by malloc, calloc, or realloc, making it available for future allocations. It releases allocated memory back to the system. It takes a pointer to the allocated memory as an argument and does not return any value. After freeing, the pointer becomes a dangling pointer, so it's good practice to set it to null. The syntax is void free of void pointer pointer. Here's an example. Int pointer numbers equals int pointer malloc of 5 times size of int. After using the allocated memory, free the memory using free numbers, and then set numbers to null to avoid accidental use after freeing. Remember these common mistakes to avoid: forgetting to free allocated memory, which leads to memory leak; freeing memory more than once, which causes double free; using memory after it has been freed; and freeing memory not allocated by malloc, calloc, or realloc. The memory visualization shows the memory before free, where 5 integers are allocated and assigned values. After free, the memory is marked as freed, and the best practice is shown. setting the pointer to null to prevent accidental use. Memory leaks occur when allocated memory is not properly freed, causing the program to consume more and more memory over time. This happens when memory is allocated but never freed, leading to gradual memory consumption, and can cause program crashes or system slowdowns. Here are the best practices to avoid memory leaks. Always free allocated memory when no longer needed. Use tools like Valgrind to detect memory leaks. Set pointers to null after freeing. And implement proper error handling with cleanup. For example, void memory leak. Int pointer data equals int pointer malloc of 100 times size of int. The function returns without freeing the memory, resulting in a memory leak, where data is lost. The memory leak visualization illustrates active memory in use, alongside leaked memory that is lost because it was not freed, and also free memory. So always free the memory. Here are some best practices for dynamic memory allocation to ensure stable and efficient C programs. Always check for null. Always verify that memory allocation succeeded before using the pointer. Always free memory properly. Free dynamically allocated memory when no longer needed. Set pointers to null after freeing to prevent dangling pointers. Free memory in the reverse order of allocation for nested structures. Implement proper cleanup in error conditions to prevent memory leaks. Use memory debugging tools like Valgrind, Address Sanitizer, Electric Fence, and memory debugging flags in compilers. Always remember, proper memory management is crucial for creating stable and efficient C programs. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.